Hey guys, good morning. Welcome to the Applied Dynamic class. Today we are going to discuss about the design thinking based spin resistant drone design challenge. Here we are going to take a drone during its failure or a motor failure. So that time how the drone is flying to maintain the stability as well as the safety. So we are going to apply the design thinking 5 stages. Like empathy, define, ideate, prototype and testing. Our student will discuss all the 5 stages and going to use the solution for the failure of the drone motors for safety and stable land.
Good morning. So when a quadcopter loses its control, it just crashes uncontrollably without any issues, without any stability. It's problems in aerodynamic and more aerodynamic and the way it is crafted. So we asked the drone hobbyists and the UAV operators what happens when during the long mission journeys. So during the long mission journeys, when the one motor inoperative takes place, it just crashes uncontrollably without stabilizing it. So they quoted that it just crashes without any more control over us. So therefore, that's where our design thinking journey begins. So when
Empathize, next is the define. Define is the framing the problem. After studying user pain points and dynamic behavior, we define our core question. The question is, how might we design an asymmetric test algorithm or fail-safe control mode to prevent spin during one motor inoperative flight? The problem connects directly to dynamic stability, especially yawing motion, auto rotation, and spin behavior. Our goal was not to fix the failure but to ensure control stable descent.
Ideate brainstorming solutions. We brainstorm possible control strategies like redistribution test among the remaining 3 motors or using differential pitch control. One idea was an AI-based fault detection system that instantly recognizes motor failure and switches to a spin-resistant mode. Another idea was slightly tilt the drone frame or use a small vertical fin to generate passive aerodynamic damping, improving yaw stability during emergency conditions. We combined these ideas into a hybrid approach, combining software-based thrust control and aerodynamic stabilization design. That's all.
Prototype about the drone simulating and building itself. We developed a simplified simulation model in lab.simulating. The algorithm detects motor loss, calculates asymmetric thrust distribution, and commands the remaining motors to balance torque. We also tested different control laws and proportional integral control and adaptive control to minimize yaw rate and angular acceleration, and simulated to show the graphs and thrust directions. We simulated graphs showed that our modified control system reduced the yaw rate by 60% during single motor failure and stabilized roll and pitch oscillation. We then built a small prototype drone using open source Zigzag flight controller and tested our algorithm in a controlled environment.
Test evolution performance. During our test, when the motor was manually shut down, the drone maintained the level attitude with only minor rotation. It didn't enter uncontrolled spin. The modified algorithm allowed for a stable auto rotation design instead of a crash, giving the pilot time to land safely. This shows how dynamic stability enhancement can be achieved through intelligent control logic without changing major hardware components.
So this is an excellent example how the design thinking help us to solve the one engine or one motor failure drone during a spin and the dynamic stability. So here all 5 stages helps to solve the problem of drone. So from theoretical to real-time solutions have been extracted from the design thinking methodology. Thank you all.